Did Ahalya join? Tell her to rejoin again, okay? Tell Ahalya to rejoin. Anyone?
Okay, ma'am.
Yeah. So we were discussing about integration-based systems, right? So if you have a question given like y of t is equal to integration minus infinity to t x of tau into d tau. So we give different inputs to the system. Okay, what will the system do? It will integrate that and it will give us back. So if I give x1 of t to the system, I get my integral minus infinity to t x1 of tau into d tau. This is my y1 of t. And if I give x2 of t to the system, I'll get integration minus infinity to t x2 of tau into d tau. Then I'll add these two, that is your y1 of t plus y2 of t. You get integral minus infinity to t x1 of tau into d tau plus integral minus infinity to t x2 of tau into d tau. So together we can write it like this. Okay, integral minus infinity to t x1 of tau plus x2 of tau into d tau. Okay, we can write together like this. So now let us add our inputs first. Okay, so I'll add the inputs. So I have x1 of t plus x2 of t. Now I'll give it to the system. The system has to integrate and give me whatever we are providing to the input. Okay. So if you give that to the system, you get integral minus infinity to t x1 of tau plus x2 of tau into d tau. Okay. As you can observe that y dash of t is equal to y1 of t plus y2 of t. Okay. So we can say that law of additivity is satisfied. Let us go to law of homogeneity now, LOH. So LOH, what you have to do is you have to multiply it with a constant, output with a constant. So if you have x of t and if you give it to the system, it will give you integration, right? Integration of x of t. So you get x of tau into d tau. So multiply that with a constant, you get k into integration minus infinity to t x of tau into d tau. Okay, this is the first result. Then next step what you have to do is you have to take x of t and multiply it with k, then give it to the system. If you multiply it with k, what do you get? You have k into x of t, give that to the system. So you get constant k into integral minus infinity to t x of tau into d tau. So we can see that law of homogeneity is also satisfied because this equation is equal to this equation. So superposition theorem is satisfied or law of superposition is satisfied. So we can say that integration based systems are linear. Got it? Can you check with differentiation based systems and tell me whether it's linear or non-linear? So take y of t is equal to d by dt of x of t and tell me whether it's linear or non-linear. You have to do it by yourself. Do and tell me, do the same way what we have done for integration based systems. Try that.
Ma'am, can you show the question, ma'am?
Yeah. Y of t is equal to d by dt of x of t. You try this and tell me it's linear or non-linear. Are they linear or non-linear differentiation based systems? Are you doing, guys?
Linear, ma'am.
It's linear, okay? So if you have input x1 of t given to the system, it will differentiate and give you that, okay? D by dt of x1 of t you get. Again, you take one more input x2 of t, give it to the system. So you get d by dt of x2 of t. So this is your y1 of t and this is your y2 of t. If you add it, you get d by dt of x1 of t plus d by dt of x2 of t. How can I write this together? Can I write it as d by dt of x1 of t plus x2 of t?
Yes, ma'am.
Yeah, I'll write it as d by dt of x1 of t plus x2 of t. So now this is our y1 of t plus y2 of t. So this is our result y1 of t and this is y2 of t. We have added that, we have got y1 of t plus y2 of t. So let us now add the inputs together, x1 of t plus x2 of t, and give it to the system. So the system should give you the differentiation of the input. So d by dt of, you get x1 of t plus x2 of t. So you can see that law of additivity is satisfied. So let us check the law of homogeneity. Okay, so that will also be satisfied, LOH also. If you multiply with a constant k, if you have x of t, give it to the system, you get differentiation d by dt of x of t. Now multiply that with a constant. So you have k into d by dt of x of t. Okay. Next step, what you do is take x of t and multiply that with a constant k. So you have k into x of t. Now you pass it to the system. So what will system do? It will differentiate x of t and give you. Okay. So d by dt of x of t. So we can see that LOH is also satisfied. So the system is linear. So what is our conclusion? Differentiation and integration based systems are linear. Okay. So I'll give you a list of few things. Okay. So you can check that. So even and odd operators or even and odd components, it's linear or non-linear. So x of t is equal to x of x e of t is equal to x of t plus x of minus t by 2, or for discrete you can take x e of n, which is equal to x of n plus x of minus n by 2. Okay. X for odd component of for continuous time, it is x of t minus x of minus t by 2. Okay. X of n is nothing but x of n minus x of minus n by 2. So they might give you something like this: y of t is equal to even component of x of t, or they'll give you, yeah, they'll give you like this, or they might give you y of t, y of n is nothing but odd component of x of n. So such systems are linear or non-linear? It's linear or non-linear? Can you check and tell me? So x e of t, you can take it like this: half x of t plus half into x of minus t. So try this and tell me linear or non-linear, even in odd components. We'll write a conclusion for this. Try that. So you have time scaling here. Time scaling based systems are linear only. So what about this? It will be linear or non-linear? Just check.
Linear, ma'am.
It's linear. Okay.
Linear,
So,
ma'am.
yeah, even and odd operators are linear, you can take, or even and odd components are linear. Okay. And yeah, even and odd components are linear, you can take. And I'll give you a few examples. Okay. So when they are non-linear, I'll tell you. So when are the linear, first we'll discuss. So the system is linear if you have time shifting and time scaling. Okay, the system is linear if you have any coefficient multiplied with x of t.
Coefficient nothing but amplitude scaling, no ma'am.
Yeah, exactly. If you have any coefficient which is a function of time or not a function of time, then those systems are linear. Okay, if you have any added or subtracted terms, they are non-linear. So whatever we have seen till now, added or subtracted terms other than input output relationship, other than x of t and y of t. So if you have, which is function of time, again another function of time also, okay, which is function of time and not a function of time. They are non-linear, okay. If you have an equation with 2t plus x of t or 2 plus x of t, those are non-linear, okay, this is non-linear. And integration and differentiation based systems are linear, okay. And we have also seen even in odd components, they are also linear, okay. And few more things few more examples I'll give you. They are non-linear, okay. You can make a list of them. Non-linear. So if you have any trigonometric operations, then it will be non-linear, okay. So if you have any sine or cos, anything like that, it will be non-linear. Suppose, for example, if you have y of t is equal to cot of x of t, then this is non-linear, okay, because you have trigonometric operation cot here, okay. Then inverse trigonometric operations are also non-linear. Are non-linear, okay. Suppose you have y of t is equal to cos inverse of something or sine inverse of cos inverse of x of t or sine inverse of x of t. If you have any such inverse trigonometric functions also, it's non-linear, okay. And if you have any logarithmic functions, it's non-linear, okay. Also, if you have any exponential functions also, it's non-linear. Okay, if you have any roots or power also, it's non-linear. Okay, you make note of this. When you are solving problems from textbook, you can correlate to these things, okay. Suppose you have y of t is equal to the root to the power of 4 x of t, or you can take y of t is x of t to the power of 4 or anything, okay. So these are all non-linear functions. And modulus is also non-linear. Modulus. So suppose if you have y of t is equal to modulus of x of t, then this is also non-linear function, okay. So these are all non-linear. Got it, everyone? So make note of these things. These are some exceptional cases. These are non-linear functions. These, if you have any trigonometric function, inverse trigonometric operation, logarithmic, exponential, roots and powers, modulus, they are all coming under non-linear systems, okay. Can make note of this. Done? Clear, everyone? Which are linear? Time scaling based systems, time shifting based systems. If you have an x coefficient which is a function of time or not a function of time, it's linear, okay. And if you have any added or subtracted term, this is also non-linear. Added or subtracted term other than x of t and y of t, then it's non-linear, okay. Clear, everyone? Is it clear? Yes or no?
Yes, ma'am.
Okay, you make note of these
Yes, ma'am.
things. When you solve, you can keep this, okay, you can keep these things in mind. If you have such things, you can directly write it's non-linear, okay. So next type of classification is invertible and non-invertible. Okay. So when do we call a system is invertible and when do we call it as non-invertible? We shall see. So before going to invertible, non-invertible, you have to know what is one-to-one mapping and many-to-one mapping. Okay. One-to-one mapping and many-to-one mapping. So one-to-one mapping means for each and every value of input, you'll have output which is unique. Okay, I'll write a definition here. For each and every possible unique value of input, output will be unique. What is the meaning of this? What is the meaning of this, guys? For each and every possible unique value of input, output will be unique. So what is the meaning of this? What does this mean, this statement? So output will not be same for different inputs. Okay. So the meaning of this is output will not be same for two or more distinct possible values of input. Okay. So we shall see this with an example. Suppose you have a set of input values here and you have set of output values here. I'll take 1, 2, 3 here and I'll take output values A, B, C. So these are the set of input values, okay, and these are the set of output values. So this is x of t. So if x of t is equal to 1, then you'll get output which is equal to b. Okay, so y of t will be equal to, if x of t is equal to 1, y of t is equal to b. Okay, if x of t is equal to 2, then y of t will be equal to a. So if x of t is equal to 3, then output y of t will be equal to c. Okay, so you can see that all three different values of input have different values of output. Okay, is it clear? Output is not the same for two inputs. Got it? It's clear? So this type of mapping is called as one-to-one mapping. Is it clear? All the three values
Yes,
of
ma'am.
input have different values of output. Output is not the same for two values of input. Okay, we shall see what is many-to-one mapping. Suppose you have a set of inputs 1, 2, 3. So these are inputs. So outputs are A and B. So I can map this to A and this also to A and this to B. So this is called many-to-one mapping. So here you can see that if x of t is equal to 1, y of t is equal to a. If x of t is equal to 2, your y of t is equal to a only, right? So if your x of t is equal to 3, then y of t is equal to b. You can observe here, for two distinct possible values of input, output is the same. Output is a only. Such type of mapping is called many-to-one mapping. Understood what is one-to-one mapping, many-to-one mapping?
Yes, ma'am.
Clear, everyone? So this is one-to-one mapping. So you can see here, for all the three different values of input, you have all the three different values of output here. Okay. So the three values of input will produce the distinct outputs. Okay. So as you can see in the next example, so two possible values of for different possible values of input, you have the same output. Okay, just a minute. Sorry for the interruption. Did you follow what is one-to-one mapping and many-to-one mapping? Is it clear? So for different values of input, you have different values of output in one-to-one mapping. Here for different values of input, you have the same output. So this is many-to-one mapping. Is it clear what is one-to-one and many-to-one mapping? Is it clear, everyone? Clear or not?
Yes, ma'am.
Yes, ma'am.
So depending on this, we'll tell what is invertible and non-invertible system. Okay. So for invertible system, there should be one-to-one mapping. Okay. So if you have one-to-one mapping, then it is invertible system, and if you have many-to-one mapping, it's non-invertible system. Okay. Take the definition for invertible and non-invertible system. So for an invertible system, there should be one-to-one mapping, okay, between the input and output at each instant of time. Got it? For a non-invertible system, there can be many-to-one mapping. Between input and output at each instant of time. Okay. So what is invertible system means, if there is a one-to-one mapping between input and output at each instant of time, then you can tell it is an invertible system, else it is a non-invertible system. If you have different inputs and you get same output, means that system is called non-invertible. For different values of input, you have to get different values of output. Okay, that is called invertible system. Is it clear?
Yes, ma'am.
So we'll take one example and we'll check it. Okay, if it's invertible or non-invertible. So y of t is equal to x square of t. So this is the given equation. You have to find it whether it's invertible or non-invertible. How do you find it whether it's invertible or non-invertible? How do you tell it's invertible or non-invertible, guys? So you have to take input x of t and give values for this input. Okay, and take y of t, check y of t. So I'll make a column. So first column I take input, second column I take output. So what is my system doing here? So if I have x of t, what is the system doing? I'm getting x square of t. The system is squaring the input, right? Yes or no?
Yes, ma'am.
Yes, ma'am.
So if you have
Yes, ma'am.
minus 2 here, what will be the output?
4.
It will be 4. If you have plus 2 also, the output will be 4 only. So it's one-to-one mapping or many-to-one mapping?
Many to one.
Many to one.
Two distinct values of input, you have the same output here. So it is many-to-one mapping and it is a non-invertible system. Got it? Clear, everyone? Is it clear?
Yes, ma'am.
So take next example, y of t is equal to x of t plus 2. Okay, so make column for x of t and y of t. So suppose your input is 0. If x of t is 0, what will be the output? You'll get output as 2, right? Suppose if I take it as 1, you'll get output as 3. If I take minus 1, you'll get output as 1. Correct? So what is happening here?
1 to 1.
Yeah, for different possible values of input, you are getting different outputs as you can see here. So this is the case of one-to-one mapping. So the system is invertible system. Is it clear? Is it clear, guys?
Yes, ma'am.
So for invertible and non-invertible, you also have a block diagram, okay? So if you have x of t, if you give it to an invertible system, you'll have output y of t, okay? That if you give back to the inverse system, you have to get x of t back, okay? You have cascaded an invertible system and inverse system, okay? So if you give the input to the invertible system, you'll get x inverse of x of t, okay? That if you give it to the inverse system, you have to get x of t, okay? This is one, just a note. So we shall check some more examples of invertible and non-invertible. So y of t is equal to modulus of x of t. So what type of system is this? Invertible or non-invertible? Try to give inputs and check what you get the output. So if you're
Non-invertible, ma'am.
it's non-invertible because you have many-to-one mapping. We shall see how do we have many-to-one mapping. Suppose if I take minus 2, what is y of t?
Plus 2, ma'am.
If I take 2 also, it's 2. So we have many-to-one mapping. So it is non-invertible system. Got it? Is it clear? So what did you understand? If you have any added or subtracted term, then it is invertible system. If you are squaring, it's non-invertible system. Okay. So we shall see some more examples for this. So y of t is equal to x of 2t. So time scaling. So tell me what type of system it's non-invertible or invertible.
Invertible.
Invertible?
Yes, ma'am.
So it's invertible system. Did everyone check this? Y of t is equal to x of 2t. So what about this y of t is equal to dy dt of x of t? What type of system is this? Invertible or non-invertible? D by dt of x of t.
Invertible, ma'am.
Check once how it is invertible.
Non-invertible, ma'am.
If I give x of t some constant 0, sorry, some constant 2, I get output as 0. Again, I'll give some constant 5. Again, I'll get 0 only, right? So it's many-to-one mapping.
Yes, ma'am.
And we had some great competition in class.
Got it? So it is a non-invertible system. So I'll give you a few more examples and we shall go to stable and unstable system. So you just tell me it's invertible or non-invertible. Y of t is equal to x of t minus 6. Then y of n is equal to n into x of n. Next you have y of n is equal to two times x square of n. Then y of t is equal to minus infinity to t x of tau into d tau. Then you have y of t is equal to modulus, we have checked, right? Yeah, these many you check. So tell me, they're invertible or non-invertible systems?
Invertible, ma'am.
Which one?
X of t minus 6.
Invertible.
Invertible.
N into x of n.
Yes, ma'am.
Wait, n into x of n, I'll give you an example. X of n and y of n. Suppose your x of n is some delta function, impulse, okay? So what do you get y of n? What is y of n?
1.
1 or what? 0 into delta n, what do you get? You get 0, right? Again, I'll take 5 times delta n. So what do you get? Five times of x of n, what do you get? It is 0 only, right? So you can see that two distinct inputs gives the same output. So it is non-invertible system. So what about third one? What about this?
Non-invertible, ma'am.
Which one?
Third one.
Yeah. So see in this. So if I take x of n and y of n, if I take x of n as 3, so what will be my output? It will be
18.
If I take minus 3 also, it will be 18 only. So it's non-invertible. It's many to one mapping, so non-invertible. What about integration based systems?
Invertible.
They are invertible. Okay. Differentiation based systems are non-invertible, whereas integration based systems are invertible. Okay. So that is about invertible and non-invertible few examples. So you can check more examples in the textbook. Okay. So now we shall move on to stable and unstable systems. Is it clear, everyone? Invertible, non-invertible?
Yes, ma'am.
Yes, ma'am.
Okay. So we shall see stable and unstable systems. So before knowing stable and unstable systems, you have to know a criteria which is known as Bibo criteria. So what is Bibo? Meaning of Bibo is bounded input and bounded output. So we have to check this Bibo criteria for systems. Then you can decide it's stable or unstable. So what is the meaning of bounded? What is this bounded input means? Bounded means you are restricting something to some particular range. Okay. So you're restricting or confining the input to some particular range. So what exactly we are limiting is we are limiting the amplitude of the input signal. Okay. So we are limiting the input signal amplitude from between minus infinity to infinity. It should be, the amplitude should be less than infinity. Okay, it should be between minus infinity to infinity. It should not reach infinity. Fine. So the amplitude of the signal should not reach infinity at any instant of time. So if you give such input to the system, so you have x of t or x of n. So that range of that x of t or x of n is less than infinity. X of n or x of t, you are giving bounded input to the system. You have to give bounded input only. Okay. If you give bounded input to the system, the output should y of n or y of t, whatever you get, should be also less than infinity. Okay, that is, it should be in the range of minus infinity to infinity. It should not reach infinity at any point of time. Then the system is called stable system. If you give bounded input, you have to get bounded output. Then the system is stable. Okay. So if this condition is satisfied, so if you are giving bounded input to the system, then you have to get bounded output. So if this criteria is satisfied, the system is stable system. Okay. Suppose if you are giving bounded input and you are getting unbounded output, that means if the output will reach infinity, then it's called unstable system. Got it, everyone? What is the meaning of this? You have to give amplitude infinity. Finite amplitude to the input. If you give finite amplitude to the input, then you have to get output which is also finite, which has finite amplitude. So if your amplitude of the output is infinite, then the system is unstable system. Is it clear?
Ma'am, output should not be infinity, right?
Yes, it should not reach infinity at any instant of time.
So that is the time it becomes unstable.
Yeah, that is unstable system. If your output reaches infinity at any instant of time, then it's unstable system. If you're giving finite amplitude to the system, you have to get finite amplitude at the output also. Okay, one condition is you have to give only finite input to the system. Okay, if the system gives you finite amplitude in the output, then it's stable. If you get infinite amplitude at the output, then it's unstable. Clear, everyone?
Yes.
So, or you can take it in terms of discrete time signals also. If input x of n is equal to some value, okay, which is less than infinity, that is given as a bounded input to the system. Okay, then if you get y of n, which is also equal to some value and is less than infinity, then the system is called as stable system. Okay, for the bounded input, if you get the output which is approaching to infinity, then the system is unstable. Got it? Is it clear? Here, whatever you are giving continuous, you take continuous value or discrete value, the amplitude should be finite. Okay, it should be less than infinity amplitude. That if you are giving to the system, you have to get output which is equal to some value. Amplitude should be equal to some value less than infinity. Then the system is stable. Okay, if the output amplitude, if it reaches infinity at any instant of time, then it's called unstable system. Got it? Is it clear? If bounded input is given to a system and if bounded output is obtained, then the system is stable. What is this Bx here? It is nothing but some value of amplitude which is less than infinity. That's it. This is amplitude of input, amplitude of output, amplitude of input, amplitude of output. Got it? It's clear?
Yes, ma'am.
So we shall see a few examples for this. Is it clear till here what is stable and unstable system? What is
Yes,
debug
ma'am.
criteria? Bounded input, bounded output criteria followed.
Yes, ma'am.
So if you're giving bounded input, that means amplitude is less than infinity of that input. Okay. If you're giving that to the system, then the system should give you the output which has amplitude less than infinity. Okay. Then it is called as stable system. If you're giving input which is less than infinity and if you're getting output which is approaching to infinity, then it's unstable system. Got it? We shall see a few examples. You'll get a clear idea. So take down this y of t is equal to t into x of t. Can you tell me it's stable or unstable system? See here, observe here, you have x of t, which is bounded. Okay, so we have to give some bounded input which is less than infinity for x of t, and we have to get y of t also which is bounded and less than infinity. Suppose I take x of t as u of t. So what is the system doing? I am giving input to the system. The system is multiplying my input t, input x of t with t. So I get t into x of t. Got it? So what if my x of t is nothing but unit step u of t? If I give it to the system, what will the system give me? It will give me t into u of t. What is this t into u of t?
Ramp, ma'am.
Ramp signal. What is amplitude of unit step?
1.
It is 1.
1, ma'am.
It's from 0 to infinity, it is 1 only. What is amplitude of ramp? What is amplitude of ramp, guys?
It is equal to t.
It is equal to t. At t is equal to 0, it will be 0. At t is equal to 1, it will be 1. At t is equal to 2, it will be 2. Suppose if t is equal to infinity, what is amplitude? It will be infinity. So it goes on up to infinity, right? So it's bounded or unbounded output?
Unbounded.
Unbounded, right? You're giving bounded input to the system, but you're getting unbounded output. So as t approaches infinity, your output y of t will also approach infinity, right? Yes or no?
Yes, ma'am.
So the system is called unstable system. Got it? Is it clear?
And we are giving infinity and checking, no, ma'am.
At t is equal, see, I'm giving unit step signal as the input to the system. I'm getting ramp. So ramp, you can see the amplitude of ramp will reach infinity, right? At some instant of time.
If you give input as infinity, then output will be infinity.
No, if I give u of t as input to the system, I'm getting ramp. Amplitude of ramp is undefined, right? It's infinity amplitude of ramp. It is t into u of t. Correct? Here you are giving finite amplitude. Okay. Here, see, in unit step, the amplitude is 1 throughout, right? From 0 up to infinity, it's 1 only. For this, is the amplitude same? Is it less than infinity? It will reach infinity at some instant of time, right? So this is an unstable system. If you are giving bounded input, you are getting unbounded output. Clear? Output is unbounded, ramp.
Yes, ma'am.
Got it? Any other doubt? If you give bounded input, then if you get bounded output, then it is stable. But in this case, this is the best example for unstable system. We are giving u of t. Okay, unit step, I'll take my x of t as u of t. U of t amplitude is 1. From 0 up to infinity, it will be 1 only. So what is the what you get? output, it will get t into u of t, which is nothing but ramp signal. So ramp signal, it is t. If a t is equal to infinity, you will get infinity only, right? Output will reach infinity when t tends to infinity. So this is unstable system. Got it? Clear? Clear or not? Clear, guys? It's clear or not?
Yes, ma'am.
What about others? Is it clear? You're giving finite amplitude, but you're getting amplitude which tends to infinity here, which approaches infinity at some point of time. So it's an unstable system, okay? Vinay, got it?
Yes, ma'am.
So take y of t is equal to x of t plus 2. So what type of system is this? Stable or unstable? So
Stable.
it's stable. Let x of t, let x of t is some value which is less than infinity. Then output y of t will be equal to some value by which is less than infinity only. Okay. So this is a stable system. Examples. You have y of t is equal to e to the power of x of t.
Ma'am, repeat the second one, ma'am.
Yeah, if you give input x of t, which is having finite amplitude, then output will be finite.
Ma'am, output
it?
will be x of t plus 2, right, ma'am?
Yeah, you're giving x of t finite means output value also will be finite only, right? Suppose give inputs for this. X of t is 2 means y of t will be 4. X of t is 4 means y of t will be 6. If you're giving finite inputs to this x of t, then output will be finite. Correct? It will be less than infinity. If you're giving inputs which is less than infinity, okay, I didn't mention like exactly, you can give any value of DC values like 6, any numbers you can give it here. Okay. So if that number is less than infinity, output whatever you get will be less than infinity only, right?
Okay, ma'am.
If your input, let your input be some value bx which is less than infinity, then output whatever you get will also be less than infinity only. Okay, you can write like this and you can say, like if input is less than infinity, then output will also be less than infinity. Got it?
Yes, ma'am.
For all the values of t. So take down, tell me this one, third one. Y of t is equal to e to the power of x of t.
Stable.
It is stable system, right?
Stable.
Yeah, let modulus of x of t be some value which is less than infinity. Then output, modulus of output, which is, it will be equal to some value which is less than infinity. Okay, this is a stable system. What about x of 3t? Try that. Y of t is equal to x of 3t. Same, right? If you are giving some finite value to the input, then output will also be finite. It will be equal to some value which is less than infinity. If you are giving x of t finite amplitude, then output will also be finite. Got it? Here, what is the system doing? You have to check this. You are giving x of t to the system. So you are having time scaling. The system is multiplying 3 for t. So you get x 3t, which is nothing but time scaling by a factor 3. Okay, if you give finite inputs, you get finite output. Got it? Finite input means amplitude is finite. Amplitude should be less than infinity. And if you give finite input to the system, then you'll get finite output. Got it? Clear, everyone? Is it clear?
Yes, ma'am.
Okay, so if you have some systems like this, y of t is equal to sine t into x of t, it's stable or unstable? You have x of t and you're giving that to the system. The system is multiplying sine t and giving you back x of t. So what is the range of sine t? Amplitude of sine t? What is amplitude of sine t? It will range from -1 to +1, right? Yes or no? It will not reach infinity at any instant of time. Amplitude of sine t is -1 to +1. So if you are giving finite input, if you are giving the input which is finite, then the output will also be finite. Okay, so it's a stable system. So if you are giving x of t some finite amplitude which is less than infinity, then output y of t, whatever you get, will also be finite which is less than infinity. Got it? Clear? Is it clear, guys? So what is the amplitude of cos and all? It's between -1 to +1, right? Amplitude of sine, amplitude of cos and all. So these are some finite amplitudes. So what if you have multiplication with sine t or cos t, then it is stable system. As
Ma'am,
long as
suppose
you
if it is tan and cot, ma'am.
yes, come again.
Ma'am, suppose if it is tan and cot.
You check what you get for tan and cot.
It will be unstable, ma'am.
It will be unstable, right? So for
Yes,
sine
ma'am.
and cos, sine amplitude is from -1 to +1. Cosine amplitude is also from -1 to +1. So if you have those, then it is stable system. Got it? Then take down this. Y of t is equal to d by dt of x of t. It's stable or unstable?
Stable, ma'am.
How? Suppose I give
Unstable, ma'am.
unit
For
step.
vertical line, it will be infinity.
Yes, come again.
If slope of the unit step will be infinity, ma'am.
If you differentiate unit step, what do you get? If I take my x of t as
Impulse
u of
function
t,
you will get, ma'am.
d by dt of u of t is impulse function. So what is the definition of impulse? Amplitude will be up to infinity, right? For impulse. Yes or no?
Yes, ma'am.
Delta t has unbounded amplitude. So it's an unstable system. Got it? Is it clear?
Yes, ma'am.
Okay. So take one more example. Y of t is equal to t square into x of t minus 1. And tell me it's stable or unstable. Is stable or unstable?
Stable, ma'am.
How? If t tends to infinity, output y of t
Oh,
also
yes,
will
ma'am.
tends to
Yes,
infinity,
ma'am.
right?
Unstable ma'am. If t tends to infinity, yes, ma'am.
Yeah, if you have any t or t square or t cube, anything multiplied with your input signal, then you can directly write it's unstable.
Yes.
Okay. And few more examples we shall see. Yeah. With respect to discrete time, n into x square of n. What type of system is this?
Unstable.
It's unstable. Okay. So here, as n tends to infinity, y of n also will tend to infinity. Okay. So it's unstable system. And take down this for discrete time. R to the power of n into u of n, sorry, x of n, where r to the power of n is greater than 1. It's stable or unstable system? Just check. R to the power of n into x of n. Sorry, where r is greater than 1. Sorry.
Unstable.
So they're telling you r is greater than 1. So as n tends to infinity, your y of n also will tend to infinity. So it's an unstable system. Okay, so and what about this one? Y of n is equal to g of n into x of n. What type of system is that? So you have magnitude of x of n, which is equal to some value, okay, which is less than infinity. What happens to y of n? It is nothing but x of n into g of n, right? X of n into g of n. It's stable or unstable? So we are giving bounded input. If we give bounded input, what do we get? What about this g of n? We don't have control on this g of n. Okay, we don't have control over this g of n. If this g of n is less than infinity, okay, if this magnitude of this g of n is less than infinity, then the output is bounded. Okay, you can write a sentence. As long as the magnitude of g of n is less than infinity, the output we get is bounded output and the system will remain stable. Got it? Clear? Is it clear, guys? Clear or not? Okay. We shall see some more examples and we'll. You have n, yeah, this is done. You have x of 1 minus n. So if you are giving bounded input to this system, which is less than, you are giving amplitude which is less than infinity, then output whatever you get will also be less than infinity. Okay, the system is stable. Clear? Is it clear? Clear, everyone? Understood?
Yes, ma'am.
Yes, ma'am.
So you have any doubts in this?
Ma'am, integration.
Yeah, tell me integration based systems.
Unstable, ma'am.
So y of t is equal to minus infinity to t x of tau into d tau. So if I am integrating so if my x of t is a cosine function, cos t, so what will be y of t? It will be minus infinity to t cos tau into d tau. So what do you get? If you integrate this, what do you get? So what do you get if you integrate this cos tau? So you get sin tau with limit minus infinity to t. Okay, if your input is cos, you get sin. Okay, so what do you get? This will be sin t minus sin of minus infinity. Correct? Yes or no?
Yes, ma'am.
So what is sin t? It is some waveform, right? What is sin minus infinity? So sin t. What is sin of minus infinity? Sin of minus infinity is minus sin infinity. So you have sin t plus sin infinity. Correct? So what happens? What is sin t? What is sin infinity here?
Zero.
So what is the amplitude here? Amplitude, so what is the DC value? So there is some amount of shifting in your sin t, right? That is sin infinity. So suppose sin infinity is some shift, DC shift, your output will be shifted by that amount of time, sin t. Got it? So as you can see here, there will be some amount of shift. So this is sin infinity, which is a shift, and sin t is a sine wave. So what is the amplitude of output? Range of sin t is -1 to +1 only, right? Yes or no? So if we take x of t as cos t, then it is stable. I'll give you one example where it is unstable. Okay. Suppose you're taking unit step x of t.
Ramp signal.
Yes.
We are
Yes,
getting
tell me.
ramp signal.
Yes, come again. I am not able to hear you.
Ma'am, if you take u of t, we get a ramp signal, no, ma'am.
Yeah, you will get a ramp signal. That is what I am about to tell you. So y of t, if you take, you will have integration minus infinity to t u of tau into d tau. So integration of unit step is a ramp signal, right? So it is unbounded output. So it is unstable. So if you have such cases where if you are giving some input, you are getting stable, and if you are giving some inputs, if you are getting unstable, then the system is unstable only. Okay. So integration based systems are unstable. So whatever input you give, it should be finite only, output should be bounded only. For some, if you get bounded, for some, if you get unbounded, then it is unstable only. Okay. So don't check this first example and think it is like it's stable. Check this also. If you give unit step, if you integrate unit step, you get ramp. So it's unstable system. In ramp signal, output will be like it will reach infinity at some instant of time. So it's unstable. You're giving stable input, but you're getting unstable output here. Unbounded output. You're giving bounded input here, you're getting unbounded output. So this system is unstable. Integration based systems are unstable. Got it? Clear?
Yes, ma'am.
Okay. So that is about stability and
Amplitude shifting, which is the function of time, is it unstable system, ma'am?
amplitude as a function of time.
Amplitude shifting, which is a function
Amplitude
of time.
shifting, suppose you have y of t, which is equal to 2t plus x of t. As t approaches infinity, output will also approach infinity, right?
Yes, ma'am.
So it is unstable, okay? Unstable system.
Ma'am, suppose if the added or subtracted term is not a function of time, no.
Then y of t is nothing but 2 plus x of t. You're telling like this?
Yes, ma'am.
As long as your input, you're giving input to the system which is bounded or which is less than infinity, output will also be bounded only, which is less than infinity. So it is a stable system. Got it? Clear? Is it clear? Followed? Stable, unstable, invertible, non-invertible systems.
Yes, ma'am.
Is it clear, everyone?
Yes, ma'am. Yes, ma'am.
Okay. So we have classified all types. Okay. We have seen all the classification and few examples, possible examples. So it's your task to go take a signal and classify it based on all these classifications. Okay, you do that. You have some problems in textbook. Okay, I've sent you the textbook video also for systems. So take a signal y of t and try to classify it based on different types of system. Okay, memory, memoryless, causal, non-causal, time invariant, time variant, linear, non-linear, and you have invertible, non-invertible, stable, unstable. Okay, you do these 6 types of classification for any given signal. Practice problems on that. Okay, so now we shall see one more topic, which is block diagram representation. Okay. This is there for your internal, so I am doing this. So in block diagram representation, we represent a system by the difference or differential equations. Okay, difference or differential equations. If it's a discrete time signal, we represent it as a difference equation. If it's a continuous time signal, we represent it as a differential equation. Okay. So based on this, you have to draw the diagram. Okay, block diagram representing the input and output values. So what is a block diagram means? It's an interconnection of elementary operations that act on input signal. Okay. It's interconnection of elementary operations that act on input signal. So block diagram is more detailed form of representation. Okay, so we use this in signals and systems. So if you have a system with the given input and output relationship, then you can represent that system using a block diagram. Okay, you have to have a input and output relationship of a system, then you can represent it using a block diagram. So block diagram consists of 3 elementary operations. Okay, basic elementary operations which are main are 3. Okay, so block diagram has 3 kinds of representation of elementary operations. So first one is scalar multiplication. So second one is addition. And third one is integration for continuous time signals, and time shift for discrete time signals. Suppose you have any, you have y of t. So which is equal to C times X of t. It is scalar multiplication. Okay, if you're having a system, you're having a signal, you're giving that to the system, that system is multiplying with a C and giving you C into X of t. Or if you take discrete time, you have X of n, if you give it to the system, it will multiply and give you with C, X of n into C. This is called scalar multiplication. Okay, coming to addition, you have Y of t, which is equal to some, if you add some signal, what happens? So you represent addition like this. Okay, so if you have X of t or X of n, if you add W of t or something, you get X of t plus W of t. Or if you have discrete time, you have W of n, okay. W of n, if you have X of n, if you add X of n and W of n, you get X of n plus W of n. Okay, so an integration for continuous time signals and time shift for discrete time signals means, so X of t, you can represent, if you integrate this, what do you get? You get Y of t, which is nothing but integral minus infinity to t X of tau into d tau. Okay, suppose if you have X of n, if you give it to the delay unit or time shift, it is represented as S. Okay, so you get Y of n, which is equal to X of n minus 1. Okay, so we represent continuous time signal in terms of integration or differentiation. We prefer integration only. Okay, and for discrete time signal, we represent by using a time shift, X of n minus 1. So given a problem on block diagram method, they'll ask you to write the direct form 1 representation and direct form 2 representation. So you have to write direct form 1 and direct form 2 representation for any X of t or any Y of t or Y of n. Okay, you will have X of t, Y of t relationship, Y of t, X of n relationship. You have to write direct form 1 and direct form 2 representation. First, we'll try to write in direct form 1 representation, and we shall see the disadvantage of this system, and let's see what is the advantage of direct form 2 representation. Okay, so take down this. Okay, question, Y of n plus half Y of n minus 1 minus 1 by 3 into Y of n minus 3 is equal to X of n plus 2 times X of n minus 1. Okay, this is a given question. So how do you write a direct form 1 and direct form 2 representation for this? This is a discrete time signal. Okay, you will have time delay blocks or shift blocks. Okay, you are having Y of n minus 1, Y of n minus 3, which is equal to X of n plus twice X of n minus 1. So what you have to do is, first try to write Y of n equation. Okay, try to write the equation for Y of n, put this other side. Okay, you have X of n plus 2 times X of n minus 1 minus half Y of n minus 2 plus 1 by 3 into Y of n minus 3. Okay, first you try to write the equation for Y of n. Okay, put whatever you have this side, put it to the other side. Okay, whatever terms you have, try to get equation for Y of n first. So what do we do in direct form 1 equation is, you have a signal X of n, you have a signal Y of n, and we have adders here. In between we have adders. So you have adders in between these X of n and Y of n, as you can see. So now what we have to do is, we have to check this relationship.
Ma'am?
Yes.
Ma'am, isn't that Y of n minus 1
Where?
in the second line?
Yeah. Y of n minus 1. I'm sorry. Yeah, it's Y of n minus 1. So what you have to do is, first write X of n input and output and write adders in between. So now you have X of n and you have X of n minus 1. Yeah, X of n minus 1 you have, right? Okay, let it be. I'll show you next problem. Yeah. So take this problem. You have x of n input and output here, and you have adder blocks here. So what is happening is you have x of n here. Okay, directly your x of n is going and adding, and you're getting output y of n. Okay. So next you have plus 2 times x of n minus 1. So you take a delay block, okay, and that is x of n minus 1. Here you have x of n. If you give it to a time delay or time shift, you get x of n minus 1 here at this stage. So that is given as the input here. Okay, and the amplitude is 2 for that. 2 into x of n minus 1 here. Okay, and check y of n. And y of n column you check. Here you have y of n minus 1 and y of n minus 3 here. So you have a shift block here. So you have y of n minus 1, right? So give it here. The amplitude is minus half. So if you have y of n, if you pass it to a shift block, you will get y of n minus 1. If you pass it to another shift block, you will get y of n minus 2. It goes like this. Okay. So again, you have one shift block. You have y of n minus 2 term here. Anywhere? You don't have, right? You have y of n minus 3. So take one more shift block. So, and you have the output, which is 1 by 3. Got it? So this is a third order differential equation. Okay, because you have y of n minus 3 also here. So how many delay blocks you are using here? It's a third order differential equation, difference equation. So you are using here x of n is directly given to the output, and you have 2 times x of n minus 1. So amplitude is amplitude is 2 with a shift in the input x of n minus 1. And this side you have minus half into y of n minus 2. You have one shift and you have amplitude minus half. Okay, and you have 1 by 3 times y of n minus 3. So shift it twice. Okay. So here you have y of n. This will be y of n minus 1. Here it will be y of n minus 2. Here it will be y of n minus 3. Okay, you have 1 by 3 y of n minus 3. So this is y of n minus 3, and you have amplitude 1 by 3. So you are giving that. So as this is a third order differential equation, difference equation, and you're having the blocks, more number of blocks here, right? So in direct form 2, what we do is, so direct form 1 consumes more number of delay blocks. So in direct form 2, what we are doing is, see here, we have x of n here, and you have an adder block. Yeah. Then you have an adder block for output. So what you do is, you reduce the number of, you write these delay blocks common. Okay. Or shift blocks, you write it common, and you interchange the outputs and inputs. Okay, wherever you have you write input side to the right and output side to the left. Okay, so here you have x of n minus 1. So this is 2 with an amplitude 2, and here you have y of n minus 1 with an amplitude minus half, and you have 1 by 3 into y of n minus 2. To the other side. So this is 1 by 3. Got it? So in direct form 2, what is happening is, we write the delay blocks, we reduce the number of delay blocks. Okay. So if it's a third order differential equation, we use 3 delay blocks. So in previous case, direct form 1, there was more number of delay blocks, right? So To reduce the time and space, so direct form 2 is useful. You can do like this. Clear, everyone? So if they give an equation like this, try to write the direct form 1 and direct form 2 representation of this equation. So you have to take input x of n, output y of n, two adder blocks, and you have write the shifting blocks here, shifting or delay block. So if you have x of n, if you shift it by 1 instant, you get x of n minus 1, delay block or shift time shift this is. Don't worry about x of t plus 1. Okay, sorry, x of n plus 1. So in direct form and direct form 1 and form 2, you use like this only. Okay, so if you have x of n minus 2, you have to shift it twice, time shift it twice. So at this stage, you'll have x of n minus 1. Again, if you time shift it, you'll get x of n minus 2. Okay, this is second order differential equation or difference equation.
Amplitude and all, you should write like that only.
Where?
Amplitude.
Whatever you have.
And
See, you have half into y of n minus 1. No, if you shift this to the other side, we just want y of n. Correct?
no, ma'am. If for y of n minus 1, if it is half, you should write like that only half.
Directly write half. If this goes to the other side, you'll have minus half, right? Right? Minus half here.
Yes,
When you're shifting. Got it?
yes, ma'am.
So this is simple, okay? So you can easily get marks in this topic. So output, whatever you have, try to get y of n. So shift all the other terms to the other side. Just take y of n. Okay? So what do you get now? So you have x of n and y of n, input and output. Write the two adder blocks here, and you have shifting here, time shifting block. So you get this equation. We represent this equation in the form of direct form 1 representation or direct form 2 representation. So seeing this diagram, we can write this equation for this equation. Okay, that is the like advantage of block diagram representation. That's it. This is for discrete time systems. If you have continuous time systems, I'll tell you what to do. Is this clear?
Ma'am, 1 second. Can you scroll down?
Yeah.
Sorry.
So try writing for this also. Take this equation and try writing the direct form 1 and direct form 2 equation. Y of n plus half y of n minus 1 plus 1 by 4 y of n minus 2 is equal to x of n minus 1. Write the direct form 1 and direct form 2 equation. Write the direct form 1 and direct form 2 representation for this given signal. Okay, so you have x of n. Try doing. So you have x of n as input side, and you have y of n. You have adder blocks for both. Okay. So you have x of n minus 1. So if you shift this by 1 unit, you will get, what do you get? You get x of n minus 1, right? You can write it. Then you in y of n side, you just check. You have y of n plus half y of n minus 1. So shift it, you have half, no, minus half. If this term go to the other side, you'll have minus half. So that will be minus half, and you have y of n minus 2 also with an amplitude 1 by 4. Take one more shift block and give amplitude minus 1 by 4 and give it to the adder. So this is direct form 1 representation.
Ma'am,
Yes,
x of n is not there in the equation, ma'am.
1
We
minute.
cannot
Yeah, just a minute. N minus 3. Okay. Here you have y of n minus 1, n minus 2, n minus 3, because you have 1 by 3 y of n minus 3. 1 minute, I'll come back to you. Yeah. So x of n is not there means you need not connect this here. If you have x of n, then do the direct connection, else you can do like this. Got it?
Yes, ma'am.
If, or you can directly write yes block here, shift block here, so that you have x of n minus 1. If you have x of n, then put a direct connection here along with this. Okay, clear everyone? So how do you write that?
Adder is not needed, right, ma'am?
Where?
Ma'am, in input side.
We need, you have to put adder both the sides, x of n and x of n side and y of n side. Okay.
And should we write arrow marks in the delay blocks?
Arrow marks, yeah, you can represent like this. Got it? You can give arrow mark like this, yeah. So this is direct form 1. For direct form 2, write these. So this is a second order difference equation. Y of n minus 2 you have. Second order. So you can need only 2 delay blocks. Okay. So put that in the between. Wait. Yeah. You have x of n and you have adder block here and adder block for output y of n. So in between you write 2 delay blocks. Write 2 delay blocks in the between and interchange this. Whatever you have on the right, put on the left. Whichever is in the left, you put it right. Okay, so this is what was the delay for that? 1, right? 1 into x of n minus 1. Yeah, 1 into x of n minus 1. So this is your output. And here, this side you have minus half into x of n minus 1. Wait. And you have minus 1 by 4 into y of n minus 2. Got it? So in direct form 2 representation, the number of delay blocks has reduced to half. If it's second order difference equation, then you need only 2 delay blocks. That's the advantage. Is it clear? So write this minus half, minus 1 by 2 and minus 1 by 4 this side. Clear everyone?
Yes, ma'am.
Okay, so we will see about for differential equations. So how to do if you have such differential equations. Okay, you take one more example for difference. So y of n plus 1 by 4 into y of n minus 2 plus 1 by 8 into y of, sorry, this is n minus 1. This is y of n minus 2, which is equal to x of n plus x of n minus 1. Okay, write the direct form 1 and direct form 2 realization for this. So you have x of n here, y of n, and you have adders for both. Okay, so these adders will be connected to each other. So you have x of n here in this equation. So you can directly connect this. Okay, then you have x of n minus 1. So one shift and you have x of n minus 1. Okay, then y of n, here you have y of n direct connection to this y of n. Okay, then you have you have a delay block, you have y of n minus 1. So that would be minus 1 by 4 into y of n minus 1. Again take a shift block or time delay block. Again you have amplitude minus 1 by 8 to the shift y of n minus 2. Got it? So this is direct form 1. As you can see, there is a difference. The order of this difference equation is 2, but we are having many blocks, right? Many delay blocks. So direct form 2 will reduce the number of delay blocks to the order of the equation. Okay, so for that, you have to write this in between. Okay, what is order of the equation? Write that many blocks in the between and interchange what is in the right and what is in the left. That's it. So you have x of n with an adder block, and here you have 2 delay blocks, and you have one more adder block here. So this is your y of n, this is x of n. So whatever is in the right will go to left and whatever is in the left will go to right. So here you have minus 1 by 4 and you have minus 1 by 8. Minus 1 by 8. And here we have 1, x of n minus 1. So it is 1. Got it? This is a direct form 2 representation. Direct form 2 is more advantageous than direct form 1 because you have the number of delay blocks less. So number of delay blocks is equal to the order of the equation, order of difference equation. Okay, is it clear everyone? Clear?
Ma'am, at output side we have to take negative amplitude, ma'am.
Where? No, you try to get equation for y of n. Put these blocks to the other side. Put these equation terms to the other side. That's all. So we have negative here. You got it? I didn't write one more step here. So y of n is equal to x of n plus x of n minus 1 minus 1 by 4 into y of n minus 1 minus 1 by 8 into y of n minus 2. Got it?
Okay, ma'am, got it.
You're putting these two terms other side, this side. So you're getting negative there. Got it? Understood direct form 1, direct form 2 for discrete time signals. So we shall see for continuous time signals we have differential equations. We shall check that. So you have d square y of t by dt square plus 3 y of t, which is equal to d by dt of x of t plus 2 times d square x of t by dt square. So what we have to do is we have second order differential equation. Second order differential equation. So what you have to do is you have to integrate this. Okay. You have to integrate twice because you have second order differential equation. So if you integrate this d square y of t by dt square twice, you get just y of t. Correct? Plus 3 into y of t you have integrate twice. Which is equal to d by dt of x of t. If you integrate twice, one integration will get cancelled with differentiation and you have just one integration, x of t into dt plus this one you have 2 times d square x of t by dt square. So that would be 2 times x of t because differentiation will get cancelled with the integration. Okay, we are integrating twice because it's of second order differential equation. So what is I try to get the equation for y of t. Okay, y of t is equal to minus 3 times double integration of y of t plus integration of x of t into dt plus 2 times x of t. Got it? So here instead of delay blocks, you are using integrator blocks. Okay, so you have x of t here and y of t here, and you are having adder block. You are having adder block here for x of t and y of t. So as you can see here, so you have 2 times x of t, so 2 times x of t. Then you have integration of x of t here. So I will integrate integration, and you have 1 into x of t. Integration into x of t. And in y of t column, as you can see, you have double integration. So you use 2 integration blocks. So and you get minus 3 amplitude here. So this is direct form 1 realization. Direct form 1 realization. Got it? It's clear?
Yes, ma'am.
So for direct form 2, same way what we did previously, do the same. You have x of t, you have a summing block here or adder block, and you have y of t. So in between I'll take the 2 integration blocks. Okay. So direct form 2 is helpful because its number of integrators are equal to the order of the system. So this is a second order system because you have d square, where is that equation, d square y of t by dt square and d square x of t by dt square. This is second order differential equation. Okay. So in direct form 2, what is the order, that many number of integration blocks you will be having. Okay. So whatever is this side, you have to get it this side. So this side you have minus 3, and here you have 2 into x of t, right? And you also have 1. Got it? This is direct form 2 realization. So direct form 2 will try to reduce the integration blocks. Okay. So here you had, it depends on the equation. Okay. Suppose you have, if you have many, if it is of direct form 3, but you have y of n minus 1, y of n minus 2, you need different, right? If you have the same on the both the sides, you need double number of integration blocks. So this direct form 2 will try to reduce the number of integration blocks here. Okay, if I give
Ma'am,
you
where
some,
is the rate 2, ma'am? In
Yeah.
form 2, amplitude. You have written 2, no, ma'am, in form 2.
Yeah.
Where should be that?
This is 2 here, right? 2 into x of t we have.
After adder, it should be.
No, here you have to write 2. Because the 2 is getting added, right? So
For y
this
of
is
t
the output.
amplitude,
Yes?
ma'am, if y of t has amplitude, where should we write?
Write it here. Got it? Okay.
Yes, ma'am.
Clear? So I'll give you one problem, you try that. For direct form 1 and direct form 2, y of t is equal to 2x of t plus 3 times d by dt of x of t plus 4 into d square y of t by dt square minus 5 into d by dt of y of t plus 7 into d square y of t by dt square. dt square, 4d square. So this is x of t, I'm sorry. Yeah. So what is order of this equation? What is order of this equation?
2, ma'am.
First order, it's second order equation. So I have to integrate twice this whole equation. Okay. So y of t, double integration of y of t, which is equal to 2 times double integration of x of t into dt plus 3 into integration of x of t into dt plus 4 into x of t. So double integration will get cancelled with double differentiation, minus 5 into integration of y of t plus 7 into y of t. So what will you do now? We have to get equation for y of t. So y of t is equal to, you have 7 y of t. So y of t is equal to, what do you get? We are shifting everything to the other side, to this side, because we want equation for y of t, right? So y of t is equal to 1 by 7 into double integration of y of t minus 2 by 7 into x, double integration of x of t. You guys following? Are you guys following?
Yes, ma'am.
Yeah. So 1 by 7 is double integration of y of t plus, no, it's minus. Minus 2 by 7 into double integration of x of t into dt minus 3 by 7 into integration of x of t with respect to dt plus minus 4 by 7 into x of t minus 5 by 7 into integration of y of t into dt. Got it? Is it clear? We are just shifting these terms to the other side, and we have 7 y of t, right? So we want equation for y of t, that 7 is coming to the denominator for all these values. Got it, guys? Have we got this equation understood?
Yes, ma'am.
Because it is second order, integrate twice, second order differential equation, integrate twice, and try to get equation for y of t. Okay? After getting equation for y of t, draw the diagram, direct form 1 and direct form 2. So you have x of t here and y of t here. So you have adder blocks for both x of t and y of t. So you have minus 4 by 7 x of t. So this would be minus 4 by 7 x of t, and you have one integration block for minus 3 by 7. So integration, that would be minus 3 by 7. Okay, I'll write it other side because we have one more integration block. Okay. Try drawing that. You have one integration block. You have minus 3 by 7 integration of x of t. So that would be minus 3 by 7. Again, you have minus 2 by 7 double integration of x of t. So one more integration block. You have minus 2 by 7 this side. And we are completed with x of t terms. Now we'll go to y of t. So you have minus 5 by 7 into integration of y of t you have. So you will have here minus 5 by 7. Again you have an,
That should be plus 5 by 7, right, ma'am?
which one? 1 minute. Oh, it was minus, right? It will become plus, correct. It was minus. So if it go to the other side, it will become plus. It's plus 5 by 7. Yeah. So that would be plus, and you have double integration of y of t for amplitude 1 by 7. So that would be plus 1 by 7. Got it? This is a direct form 1 representation. Clear?
And can we write amplitude 7 in y of t and remaining fractions as integers?
I didn't get you. Amplitude?
I mean, instead of fraction, can we write 7 y of t equals to equation?
7 y of t is equal to that. So you have to write for y of t only. Equation you have to write it for y of t. So we are putting that 7 other side. Got it?
Yes, ma'am.
You write like this only. Try to get equation for y of t alone. Okay. This is direct form 1 representation. So as you can see, for second order differential equation, you are having 4 integration blocks here. So if we use direct form to realization, then our integration blocks will get reduced to 2. Okay. So in direct form to representation, so you have x of t, adder, and in between those two adders you have integration blocks 1 and 2. For second order you'll have 2 integration blocks. Okay, so whatever terms are there this side, shift it to the other side, and whatever are there to the left, shift it to the right. Okay, so here you have 5 by 7 plus 5 by 7, and you have 1 by 7. Write the arrows here, and other side you have minus 3 by 7, and you have minus 2 by 7, minus 3 by 7 and minus 2 by 7, minus 3 by 7 and
Ma'am, can you finish today's class, ma'am? It's 5:15.
yeah, it's done. Minus 2 by 7. Okay guys, this is a direct form to representation. Here the blocks, number of integration blocks will be equal to the order of the differential equation. Got it? So these are your syllabus for your internals. Understood everyone? Direct form 1, direct form 2. Is it clear?
Yes, ma'am.
Okay, so if you have like this, you have to do like this. For difference or differential equation, try to get equation for y of t or y of n. Draw the corresponding time shifting blocks or integrated blocks. Okay. So this is just an introduction for you. So these type of direct form and direct form 2 you will be using for Z transforms also. To have an introduction for you in unit 1, just we are doing this. Okay. I'm sorry guys, I took a lot of time. You can write your name and USN in the chat box. If you have any doubt, you can contact me, okay? So try solving problems from textbook. Direct form and direct form 2, you refer this only, this video, that is enough. It's not there in textbook for continuous time and discrete time. It's there in Simon Hakin. But it's not so clear. You can try to refer that if you want. Or you can just follow this this class, whatever I have done.
Okay,
If you have any doubts,
thank
you
you,
can
ma'am.
contact me. Thank you, students.
Thank you, ma'am.